Welcome to Mathematics with Tom. I am Tom, and today we are going to take a look at eigenvalues and eigenvectors. Well, here's what I want to show you. So far in studying solving systems of equations, we've found that we were given some differential equation that say something of the form capital Y prime equals A times capital Y, where we said that capital Y prime, this is the vector of we have maybe y1 prime of t, y2 prime of t, and so far we've looked at just systems with two equations, but you could have systems that go on and have even y sub n of t. So the components of the y prime vector are functions of t, and similarly, y, or you could think of this as y of t, is the vector of y1 of t and y2 of t. And it obviously needs to match with y prime, so in this case, we would have y sub n of t functions. Okay, now a, so in this case, since we have n functions, then and A is an n by n matrix. And it's from there that we are going to solve these systems of equations. Now, here's what else we found. We found that the solution y, or y of t, y is equal to, it has some scalar, we'll just call it c, and then there's an exponential e, and we're going to call that lambda times t, and then it has some vector. So we're just going to look at the 2 by 2 case, but we'll just call it some vector v. That's a boldface v. Okay, so for v, a vector. Okay, now let's see how this works. So look at that. If that's y, that solves it, then this means that y prime, capital Y prime, would equal lambda times c times e to the lambda 2, or t times my vector v. Well, what else does this mean? This also means then that if I take a times the vector y, well, what does this give me? Well, and what we've discovered is that this gives me the case that y is actually what we called an eigenvector, and the eigenvector gives me some... Oh, I'm sorry. I got ahead of myself. Okay, now let's see if we can solve this problem. So we have this problem where on the left-hand side we have our solution is... Oh yeah, okay. Sorry, I got off course. Let's get back on course now. No messing around here. All right. Y prime. So let's just solve the equation that we have. So I'm going to plug these back in. So I'm going to plug in my y prime and my y back into the original equation. And let's see what happens. So this says then that I'm going to go back to this equation. So I'm looking at y prime equals a times y. Well, y prime is lambda c e to the lambda t times the vector v, and that is equal to, we said, the matrix A times the vector y. Well, the vector y, we said, is c e to the lambda t times the vector v. Well, let's continue on from here. Notice that c e to the lambda t is common on both sides. It's very simply a scalar, so I can clean this up, and I'm going to write this as lambda times v is equal to a times v. So I'm just dividing the scalar out. Now, we can do that with scalars. We can't do that with matrices or with vectors. So we're down to this equation of a times v equals lambda v. Well, it does not solve using the same strategies. So what we have to do is another one. Let's do this. Let's take a little insight. So before we're sure of what to do, insight. Remember, we spent our time in this class, we began out as y prime equals a y. But what we found is, and then what we did is we added q. Well, when q equals 0, then this could also be rewritten as y prime minus ay equals 0. And what did we find then? Well, then y is y sub n. It's the null solution. Well, let's take a look at our problem. Our original problem says that y prime equals a times capital Y. Well, let's just use, instead of a lowercase q, what if we had some capital Q, where that was some additional input function? Well, if that's the case, and we said that this input vector of this vector of input functions, what if that's just the 0 vector? Then what are we finding? Then capital Y is capital Y null. That's it. We're solving the null equation. Well, if that's the case, we know how to do that. That's when it equals 0. So I'm going to write this as AV minus lambda V equals 0. There's the null solution. Now, this is where it gets fascinating. Remember, A is an n by n matrix. V is just a column vector with n components. So you can't factor V out directly. But what we can, and this subtraction only makes sense if there's a matrix, or a vector minus a vector, or if I want to factor it, then I'm going to need a matrix minus a matrix as my result. So I'm going to do something that is completely legitimate, and that is, we have the identity matrix. It's no different than multiplying by 1. So what if I write this as A times V minus lambda times I times V equals 0? Well then, now look at this. This is lambda I is a matrix. A is a matrix. They're both being multiplied on the right by the vector V, so we can factor to the right. So this is A minus lambda times the identity matrix times V equals 0. And here's where it gets even better, because what is this? A minus lambda I, it's a funny way to write it, but that whole piece is a matrix. Okay, now, an eigenvector, we're after non-trivial solutions. So when let's do this, when V equals 0, this is a trivial solution. It doesn't tell us anything about the system. Well, what if but when V is not the 0 vector, I'm even going to put a vector symbol just to make sure we don't forget that V is the 0 vector. So when V is not the 0 vector, well, what does that mean? That means that A minus lambda I has to have some dependent columns inside of it. Well, if A minus lambda I has dependent columns in it, well, one of the properties we learned about the determinant is that when V is not 0, let me write this out, then A minus lambda I must be singular. i.e., oops, that's a dot, i.e. has dependent columns. Well, if it has dependent columns, then what do we know? Then the determinant of A minus lambda I has to also be 0. And that is how we solve for the eigenvalues. This gives the eigenvalue solutions. I hope that helps, and thanks for watching.